Hello friends, welcome to our channel Crash Course for Engineers. Today's topic is related to fluid dynamics. Now this fluid dynamics is the study of fluid motion and the forces acting on fluids, which includes liquids and gases. Here we go through the concepts like pressure, velocity, and the density. Now, the applications of fluid dynamics are varied from designing the aircraft to understanding the weather pattern. There are two sub-disciplines of fluid dynamics. First is aerodynamics, which includes the study of air and other gases in motion, and hydrodynamics, the study of water and other liquids in motion. So we'll go to the basics. We'll talk about what are the forces acting on the fluid. We know that as per the Newton's second law of motion, the net force, that is Fx, acting on a fluid element in the x direction equal to the mass m of the fluid element multiplied by the acceleration ax in the x direction. So mathematically we say F is equal to ma, that is Fx is equal to m into ax. Now in case of the fluid flow, the forces which are present are: first is the gravitational force Fg, second is the pressure force Fp, then viscous force Fv. If there is a turbulence, there will be turbulence force Ft, and the force because of the compressibility, so Fc. Hence, the net force acting Fx is equal to Fgx plus Fpx plus Fpx plus Ftx plus Fcx. Now, that can be said to be equal to m into ax. Okay, now what we are talking about, if the force due to compressibility Fc is negligible, the equation for the Fx, that is resultant net force Fx, will be equal to Fgx plus Fpx plus Fvx plus Ftx, that is gravitational force, pressure force, viscous force, and the turbulent force. Now, this equation of motion is called as the Reynolds equation of motion. Now, next thing, suppose the turbulent force is negligible, then the equation change. So, what we will get, Fx is equal to Fgx plus Fpx plus Fvx. Now, this equation is called as the famous Navier-Stokes equation. Now, in the Navier-Stokes equation, if we are assuming that the fluid is ideal, viscous force Fv is equal to 0. Hence, the equation will be modified into Euler's equation of motion. Fx is equal to Fgx plus Fvx. Now, there is a simple derivation which is related to the Euler's equation of motion. Now, for that, as per the previous discussion, we know that this equation of motion, in which the force due to gravity and force due to pressure are taken into consideration. This can be derived by considering the motion of the fluid element around a streamline. Now, what we'll do, we'll consider a streamline in which the flow is taking place in S direction. So you can see here there is a streamline and the force is taking place, the flow is taking place in S direction. Consider a cylindrical element of cross section dA and length ds. Now this is the cylindrical element. This is the cylindrical element of cross section area dA, and suppose this length is ds. The forces acting on the cylindrical element are the pressure force Pa in the direction of force, in the direction of flow. So P dA, this is the pressure force in the direction of the flow. There will be opposite pressure force, opposite to the direction of flow. So that will be equal to P plus dabba P by dabba S ds into dA. So this will be in the opposite direction. Then there will be weight of the element rho g dA ds. So here there will be the weight of the element rho g dA ds. Let theta be the angle between the direction of the flow and the direction of action of the weight of the element. So, so this angle we are assuming it as a theta. The resultant force on the fluid element in the direction AS must be equal to the mass of the fluid element into acceleration in the direction S. So that we have seen in the previous slide. So F is equal to ma is equal to pressure force plus force because of the gravity. So this is the Euler's equation of motion, so that we are deriving. So putting the values in the equation PdA. So in our diagram, so PdA was in the upward direction. So this is the PdA minus P plus dabba P by dabba S into ds into dA. So in other direction, opposite direction was this pressure force. So the sign is negative here. Minus rho g dA ds cos theta. The weight element of the weight is equal to rho dA ds into as. So this is the equation if we put all the relations in the equation, where as is the acceleration in the direction of s. We know that acceleration is equal to rate of change of velocity, so dv by dt. Here we know that v is the function of s and t. So acceleration is equal to dabba v by dabba t can be written as dabba v by dabba s into ds by dt plus dabba v by dabba t. If we put ds by dt is equal to v, if this is v, the equation will become v dabba v by dabba s plus dabba v by dabba t. Now understand, there is one small assumption we are doing. If the flow is a steady flow, so dabba v by dabba t is equal to 0. So it is a time dependent system, independent system. So as is equal to v dabba v by dabba s. If we put the value of as in this equation, so minus dabba p by dabba s dA ds. So this equation will change. So P dA minus P dA minus dabba P by dabba S ds into dA. So this will get cancelled out. Only negative term will remain. So here it is written dabba P by dabba S into ds dA minus rho g dA ds cos theta. This term is equal to putting the value of acceleration in the s direction, dabba v by dabba s, rho dA ds into dv by dabba v by dabba s. If we divide this equation, we know that there is something common. So rho dA ds can be said to be common. If we dividing this equation, it becomes minus dabba p by rho d dabba s minus g cos theta is equal to v dabba v by dabba s. Rewriting this equation, dabba p by rho dabba s plus g cos theta plus v dabba v by dabba s is equal to 0. But by the triangle, if we look at this triangle, cos theta can be written as dabba z dz by ds. So if you look at this triangle, this small triangle, we can say, so it is equal to theta, cos theta is equal to dabba dz by ds. Putting this value in the above relation, so 1 by rho dp by ds plus g dz by ds plus v dv by ds is equal to 0. Or I can say that dp by rho plus g dz plus v dv is equal to 0. Now this equation is known as the Euler's equation of motion. From this Euler's equation of motion, we can derive the Bernoullis theorem. If we integrate the Euler's equation of motion, what we are getting? Integration of dp by rho plus integration of g dz plus integration of v dv is equal to constant. Now we are assuming that the flow is incompressible, so rho is constant. So here we are getting integration of dp is equal to p, so p by rho plus gz plus v square by 2 is equal to constant. So this equation is known as the Bernoullis equation. So P by rho g is called as the pressure energy per unit weight of the fluid, or in simple words, we call it as a pressure head. V square by 2g is called as a kinetic energy per unit weight or kinetic head, and Z is the potential energy per unit weight, or in simple words, we call it as a potential head. Now, if we look at the Bernoulli's equation or Bernoulli's theorem, we say that there are some assumptions. We are talking about ideal fluid, so viscosity is zero. We are talking about flow is steady. We are talking that incompressible flow is there and irrotational flow is there. Now, next is the Navier-Stokes equation for real fluids. Okay. After this, we'll try to solve a very simple numerical which is based on the Bernoulli's theorem or Bernoulli's equation. So for solving this kind of numericals, the student should have the understanding of Bernoulli's theorem. He should know what are the terms which are in the Bernoulli's theorem and what is the interpretation of those terms. Water is flowing through a pipe of 5 centimeter diameter under a pressure of 29.43 Newton per centimeter square. So gauge pressure is given with a mean velocity of 2 meter per second. Find the total head or total energy per unit weight of the water at cross section, which is 5 meter above the datum line. So this is a very simple numerical, straightforward numerical. We'll uh, write one by one things which are given. So here given things are the diameter of the pipe D is given as 5 centimeter. We use meters for the for the dimensions. So it will be 0.5 meters. Then pressure is given. So P is given as 29.43 Newton per centimeter square. So I can write it as 29.43 into 10 to the power 4 Newton per meter square. Then velocity is given as 2.0 meter per second, and datum head, so head is given as 5 meter. So uh, we are asked to find out the total head or total energy per unit weight of the water at cross section. Okay, so the total head, the formula can be written as total head is equal to, first we talk about the pressure head, second we talk about the kinetic head, and third we talk about the datum head. Okay, so we'll go to the next slide. So pressure head, the formula was P by rho into G. So 29.43 into 10 to the power 4 divided by density of water is 1000 into value of G is 9.81. So the pressure here is found to be 30 meters. Please calculate the value. Then we need to find out the kinetic head. It is equal to V square by 2G. So V, so 2 square and 2 into 9.81. So the value is 0.204 meters. Okay. And the uh, third one was the datum head. So Z value is already given 5 meter above the datum line. So total head we can say will be the summation of all these heads. So P by rho G plus V square by 2G plus Z is equal to 30 plus 0.204 plus 5. So students, what is the answer? 35.204 meter is the answer. Now, if we closely look at the numerical, this is the very straightforward numerical, and many things are given in the numerical, so it was not a big issue to solve this kind of numerical. Now, next, we'll try to understand one more and numerical. So, now what he is telling in the numerical, water is flowing through a pipe of diameter 300 millimeter and 200 millimeter at the bottom and the upper end respectively. The intensity of the pressure at the bottom end is 24.535 Newton per centimeter square, and the pressure at the upper end is 9.81 Newton per centimeter square. Determine the difference in the datum head if the rate of flow through the pipe is 40 liter per second. Now, if we look at this numerical, first we'll talk about the diagram. So, determine the difference in the datum head if the rate of the flow through the pipe is 40 liter per second. Now, there are two ends of the pipe. One can be said to be the upper end, and second can be said to be the bottom end. Now, it is specifically given in the numerical The diameter at the bottom end is 300 millimeter and at upper end is the 200 millimeter. So if we draw this diagram, this can be like this one. Okay, so diagram may be like this. Okay, so this can be the diagram. So we will say that suppose this is the end 1 and this is end 2. The diameter is given. So D1 is given 300 millimeter, 0.3 meters. P1 is also given. So we'll talk about P1 is 24.525, 24.525 Newton per centimeter square is equal to 24.525 into 10 raised to the power 4 Newton per meter square. This is about section 1. Now talking about section 2, diameter is given as 200 millimeter. So we'll say 0.2 meters and the pressure is given, P2 is given 9.81 Newton per centimeter square. So conversion into Newton per meter square 9.81 into 10 to the power 4 Newton per meter square. Also, the flow rate is given. We know that flow rate is denoted by Q. So Q is equal to 40 liter per second. What we'll do, we'll convert it into meter cube per second. So it is equal to 40 upon 1000. If you have referred my previous channel, the conversion rate is already given from liter per second to meter cube per second. So 0.04 meter cube per second. Now, in by the continuity equation, we know A1 V1 is equal to A2 V2. So V1 is equal to 0.04 upon A1 because we know the flow rate is equal to 0.04. So putting this value equal to 0.04 divided by pi by 4, 0.3 square. So the velocity will be equal to 0.5658 meter per second. Same way I can find out V2 is equal to 0.04 by A2 equal to 0.04 divided by pi divided by 4 into d2 square. So d2 is equal to 0.2 cos square. So what we are getting, the velocity is equal to 1.274 meter per second. Okay, so this part that we have got, we have got the values of velocities at 1 and velocities at 2. Now we, if we apply the Bernoulli's equation, so what will happen if we apply the Bernoulli's equation? Just 1 minute. So we'll apply the Bernoulli's equation P1 by rho g plus V1 square by 2G plus Z1. This is equal, this is the inlet side is equal to P2 by rho G plus V2 square by 2G plus Z2. Now putting the values step by step, we'll solve the numerical 24.525 into 10 to the power 4 divided by 1000 into 9.81. That's why we have solved one simple numerical on the basis of this theory. So now 0.566 square divided by 2 into 9.81 plus Z1. Okay. Now we don't know the value of Z1. Next is 9.81 into 10 to the power 4 divided by 1000 into 9.81. This is P by rho G, P2 by rho G plus 1.274 square, V2 square by 2G, 2 into 9.81 is plus J2. So what we are getting here, 25.32 plus Z1 is equal to 11.623 plus Z2. So I can say that Z2 minus Z1 is equal to the subtraction of 25.32 and 11.623 will get the answer is 13.70. Now we have applied the Bernoullis equation in a simple words, and the numerical was very simple. Okay, now we'll go to the next part, that is Bernoullis theorem for real fluid. As we have seen in the Bernoullis theorem part, we have given some assumptions. So here, the Bernoullis equation was derived on the assumption that the fluid is non-viscous and therefore it is a frictionless flow. But we all know that all the real fluids are viscous and hence they offer the resistance to flow. Thus, hence there are always some losses in the fluid flows, and hence in the application of the Bernoullis equation, these losses need to be taken into consideration. Then the Bernoullis equation for real fluids between points 1 and point 2 can be given as V1 by rho G plus V1 square by 2G plus Z1 is equal to P2 by rho G plus V2 square by 2G plus Z2 plus HL. Now, what is the HL here? Where HL is the loss of energy between points 1 and 2. So, this is the Bernoullis equation for the real fluids, where the term is added for the losses. We'll go to a very simple numerical to understand what will be the losses, right? A conical tube of length 2.0 meter is fixed vertically. So now, if we talk about a conical tube is fixed vertically. The length of the tube is given 2.0 meter with its smaller end upwards. So it gives us the understanding of the tube. We can say it may be like this. The velocity of flow at the smaller end is 5 meter per second. So this velocity, if we say this is one end, this is two end, while the lower end velocity is 2 meter per second. The pressure head at the smaller end is 2.5 meter of liquid. Now this term is added. The loss of head in the tube is 0.35 V1 minus V2 whole square by 2g, where V1 is the velocity at the smaller end and V2 at the lower end respectively. Determine the pressure head at the lower end. The flow takes place in the downward direction. The flow is taking place in the downward direction. So we'll put the values which are things given in the numerical. So L is given as 2 meter. Now V1 is given, so 5 meter per second. Now in the numerical, uh, pressure head is directly given. So P1 by rho G is equal to 2.5 meter of liquid. Now V2 is given 2 meter. Okay, so head loss due to friction. Okay, so 0.35 V1 minus V2 square by 2G. If we put the values, what we are getting, HL is equal to 0.35, 5 minus 2, 5 minus 2 square by 2 into 9.81. So what we are getting, 0.35 into 3 square, that is 9. We can put 2 into 9.81. So it is equal to 0.16 meter. The losses are there. So what will be the pressure head? Pressure head we want to find out is equal to P2 by rho G is equal to what? So if we put the Bernoullis equation, so P1 by rho G plus V1 square by 2G plus Z1 is equal to P2 by rho G plus V2 square by 2G plus Z2 plus HL. Now here what we can say, there is nothing given in the numerical regarding the datum line. So if we say that the bottom section passes through the datum line, so this will be at 0, 0 and this will be at 2.0. Okay, so Z1 will be equal to 0 and Z2 is equal to 2.0. So putting the value 2.5 P1 by rho G, V1 square by 2G 1.27 plus Z1 2.0 plus, so now this is equal to, okay, this is equal to P2 by rho G is unknown plus V2 square by 2G 0.203 plus Z2, that is the value will be equal to, Z2 is equal to 0 plus HL, the value of HL was uh, 0.16. 0.16. So we have calculated the value of HL here. If you remember, so 0.16. So by this, I can get the value of P2 by rho G is equal to 5.407 meter of fluid. So this is the answer. Now, friends, please solve these numericals on the Bernoullis equation, Bernoullis theorem. These are very simple and numericals if you understand the Bernoullis equation, which has pressure term, velocity term, and the datum head term. And if you have any queries regarding this theory and the numerical part, please put it in the chat box. If you like the content, please subscribe the channel. Thank you.